Hello. Okay. In this lesson, we are going to study the two variable case, okay, which is a bivariate distribution. Let's say the definition. Okay. The bivariate distribution, let x and y be random variables. The joint distribution or bivariate distribution of x and y is the collection of all probabilities of the form probabilities p probability x y is in the set C, okay, for the pairs of real number, so that this one is even. So you notice that this one accommodates both discrete and continuous, okay. So let's see the topic that we will discuss today. So first, we will talk about the discrete case. Second, we will talk about continuous case. The third one, we will talk about the mixed type. So if there are two, one may be discrete and other may be continuous, and that's possible, okay. And the first one, we apply the concept that we learned earlier about the cumulative distribution into this kind of setting also, okay. So first, discrete joint distribution. Let x and y be random variables and consider this order pair. If there are only finitely, okay, definition is very similar to the one variable case. Let's say only finitely. Okay, let's see. Only finitely or countably many possible values. Okay, so we say that that one is a discrete joint distribution. Okay. Suppose that two random variables each have discrete, x and y have discrete. Because if they are finite, let's say, where is my pen? Okay. If x finite and y finite, then Cartesian of x and y must be finite also, and that holds true for the countable case. Okay, if x is countable or y is finite or countable, that's fine, but x Cartesian with y must be countable. So that's fit the definition. So I would like you to think about one question. Okay, is this true for the continuous one? Let's say if x is continuous, okay, my question is this: if x is continuous, y is continuous, that mean that x Cartesian y is continuous. Or in other words, this function that is satisfy the continuous distribution. Okay? What do you think about it? And I will tell you answer soon. Okay? So the joint probability distribution on the joint PF of x and y is defined as a function f such that for every point x, y in the xy plane, this one. So this very similar, okay, very similar to the lesson 14, okay, if we compare the definition. If x and y have discrete, if x, y is not one of the possible value, then it is equal to 0. That means it is not belong to the Cartesian product, right? Also this one, and also this one. Very, very similar, okay? Very similar to the one variable case, okay? Next one, continuous distribution. So, two random variable x and y have continuous joint distribution if the x is a non-negative function f again. This one, let me use the shape. This one, very similar, okay? And this one can be defined as this one, very similar. And the two properties, this one, very similar. And this one, almost the same, except that we just extend from one variable case to two variable case. Okay. Next. For every contribution of the xy plane, additional property is one solve too. Okay. And for every individual point, okay, every individual point and every infinite sequence of point of xy as probability 0. That is individual point that is finite, okay, and countable. So for finite and countable set, the sum of the property sets. So let's say if set C is either finite or countable, probability that x, y in C is equal to 0. That's the property. Okay. The second one is that let f be a continuous function of real variable defined on possibly unbounded x, a, b. And if we define the function, okay, if we define the function, even though it is y of x, let's say y is a function of x, x is a function of y. So we pick the point that is the function, okay. This one has probability of 0 also. It's just like a line, okay. So if we think about, let's say in two case, let's say about the normal curve. We know that for finitely many points, it is 0. For, let's say, for a sequence, let's say, from this one point, and convert to this one is a sequence, right? This one is still 0. And if we take, okay, if we take a line that cut to this, okay, a line that cuts to this, only this line, okay, so only this line. So this one, the probability must be 0 also, okay. So let's go back to the question that I've asked earlier. If x has the continuous distribution, and let's say we define that y is equal to x, okay, y is equal to x, then both x and y have continuous distribution. So should they have bivariate continuous distribution? But, okay, so x is the continuous, y is the continuous, but they are the same. So the probability that this lies on the line, okay, lies on the line. So this one is that y is fx, okay, fx, and fx equal to x. This one has the probability of 1, okay. So the line must have the probability of 0, right? But in this case, the probability of this particular line is 1. So this one are not, okay, are not the joint continuous distribution, okay. So continue. So the second example, suppose that the joint PDF of x and y is specified is this one. So we determine constant C and the probability, okay. So this one, okay. This integral from minus infinity to infinity, but take a note that this one, okay, outside this range, this one is not the support. This one is not support, okay. So we have to, okay, we have to look at this one instead. This one may be the support. So we have to consider in this case. And in this case, okay, in this case, we are going to take the integral. It's a double integral because we have to find, let's say, the volume, okay. For C, x squared, y, let's say dy dx, okay? But the important thing is that what should be the above and below, okay? So we know that y is a support, okay? Support from x square and 1, okay? So y is between x square and 1 from this one, okay? From this one. But what should be x? I didn't say here. But if we can imply this condition, so this inequality implies, I will write above, okay, implies that x squared is less than or equal to 1. In other words, x between -1 and 1. And this is the area that we're interested, okay? So this one we can plug in -1 and 1 here, okay? -1 and 1 here. So double integral is not difficult, okay? I think you have reviewed it already. So the c is equal to 21/4. And probability of x greater than or equal to y, okay? So we will start slowly with this example, okay? So let's say y, okay? Y. We know that y ไม่มี greater than or equal to x square. Y greater than or equal to 1. And y less than or equal to x. So this one is the lower bound. Okay? And this one is the upper bound. These two conditions. So we can write the minimum between x and 1. But there are no restriction on x because x between -1 and 1. So we can plug in this -1 and 1. And we know that the minimum between x and 1 is x. Is x. But in other case, you may not be lucky and you have to separate it later. But I think that there are practice problems that you will find in this situation. And I will tell you later. Okay? So let me start with the simple case. So let's go to the mixed variance distribution. Let x and y be random variables such that x is discrete, y is continuous. Suppose that is a function f such that this one holds true. So if not is mixed, but we require what? We require the f here. F here, okay? F here. And since x is what? X is discrete. Discrete refer to the sum. Okay? And we know that y is continuous. Okay? Continuous, that means you're going to take the integral. So it's just the mix between the sum and integral. But can we write in the inverse? Yes, because the integral we can switch the order. So the sum and integral we can switch the order. Okay? So we can write it out like this. We can write it like this. Okay? We can write it like this. That's all. Next. Okay? For the mixed probability distribution, so we can compute such that Cx is this one, okay? Cx. So we can do it like this. So x equal to c. Then we have to find the Cx first. This is very similar to the last example, all right? Cx, and then we sum all the x that we're interested in. And we can define similarly, okay? Okay, so let's see the example. Suppose that the joint PDF or PF of xy is this one, okay? And y we will check that this one is actually PF or PDF, okay? So let's say in this solution, we take the integral first because y is continuous. Okay, y between 0 and 1. So this one. And we sum, okay? So we integrate with respect to y disappear. So this one is a function of x. It's a function of x, okay? It's a function of x, and we sum from x equal to 1 to 3, and it must be equal to 1. Okay, you can check it by yourself. That's simple, the integration. Okay. How about calculating this? I've said before, we can take integral and then the sum, or the sum and then integral. If we use the same answer, okay, you can check it by yourself. Okay, the next concept, bivariate cumulative distribution function. So, the first one we have, the first variable case, we have this one, only this one, okay? And for the two variable case, we have this one, okay? So how do we calculate this? Let's say from, okay? So, let's say, if we want to find this, so we have separate this statement into this one and this one, okay? And this statement, we can split into this one and this one, okay? Similarly, and for this chunk, okay, from this chunk is FBD, this chunk FAD, this chunk BC, this chunk is AC. So let's think about the rectangle. A, B, C, and D. Okay. So BD is the whole, right? The whole minus this side, and minus BC this side, and plus this side, and we will get this rectangle. Okay. Okay. Next, going back and forth, we have CDF. We can go to PDF. We have PDF. We go to the CDF. Okay. So if we have the joint CDF of x and y, and we want the joint of only f, we take the limit. That is, we have the joint f is a function of x and y, right? And we want only x. We want to get rid of y. We can get rid of y by taking y into the infinity. Similarly, if we want to get rid of x, okay, we want to find cumulative distribution of y, we can take x to the infinity. And this one, we go to the PDF to CDF. This is just the double integral, okay? And if we want to take the CDF to PDF, we have partial derivative for 2 times, okay? Okay. Next, example 4. Suppose that x and y are random variable that takes value only this, blah, blah, blah. Suppose that the joint CDF for this one and this one. So, determine F1. So, F1 is f as the function of x. Okay. So, we have to get rid of y by taking y into infinity. And since we have CDF, we can call it PDF by partial derivative for 2 times. Okay. So first, we have to define the cases. Okay. So y less than 0, 0. Y greater than 2 and x greater than 2 is 1. Okay. So x between 0 and 2 and y greater than 2. Okay. So we have this one. This one, okay. This one, okay. This one come from this one. Okay. So because Oops. Because we know that, okay, we know that if y greater than 2, f xy is equal to fx2, if equal to fx2. Similarly, is f xy at this case is equal to what? 2 and y. Okay. So if we take, so if x less than 0, 0, if x greater than 2 is 1, simple. Okay. But if we want to get this one, okay, if we want to get this one, we do this by, since we know this, okay, we know this. You know that this is the CDF of x and y when still x between 0 and 2. And y greater than 0 is the same as y go to infinity because the support ends at y equal to 2. Okay? So this one is as if we take y go to infinity. So this one is the answer to this one. Okay? Okay. So take partial derivative 2 times. Okay? So we have seen that we can going back and forth PDF and CDF, and we have seen mixed distribution. And we will see more in the upcoming lesson. So stay tuned.